All right. Great. So it is a pleasure of my career to have worked with John Shelf back in those days, and I'm really pleased to be here. I'm here, I think a lot of you will enjoy this, at least I hope so. We're going to give both a retrospective in one of the great discoveries of physics of the last century, I think it's fair to say actually, and how high-performance computing played a major role in getting us there, and how it also helped drive high-performance computing and many things that are happening these days that go well beyond the original high-performance computing. So this is a talk by 5 of us all together. So the first section will have myself talking a little bit about the history and how we got to the initial stage of what became the great discoveries of colliding black holes and gravitational waves. Gabrielle Allen will then go on to talk about some software developments that were extremely important in bringing communities together. Manish Parashar will talk about the connection of that work to computer science and how that drove computer science and also helped enable the physics itself. Luciano Rozzola will talk about the current state of the art of gravitational wave source simulations, including black holes and neutron stars. And Nelly Huerta will talk about advances, particularly very recently in artificial intelligence, AI techniques, and how that is helping to accelerate this entire field. So, as we get started, I want to point out a couple of things. The middle picture, I'm very proud to have been slightly associated with a postage stamp, a visualization of gravitational waves from colliding black holes. Actually was on a German postage stamp in 2017. And on the right-hand side there, you can see Physics Today, the cover, and I will zoom in on that in just a minute. Here we go. So this is very, very exciting. I literally cried when I saw the results of this. This on the right is a Physics Today article on what's called the history or the story of a momentous paper about the discovery of gravitational waves in black holes. Einstein predicted in 1915, laid out his general theory of relativity. Shortly thereafter, there were predictions of both black holes and gravitational waves, but they weren't understood at all what they meant or even if they were real. And then I would just say many years later, in fact in 2017, a Nobel Prize was awarded for the discovery of gravitational waves from 2 colliding black holes. And at the top there, this is from a detector in the United States called LIGO. There are 2 detectors, one in Louisiana and one in Washington State. The top panel, Hanford, Washington, and Livingston, Louisiana, shows the actual experimental data. So that's a waveform of gravitational waves that roughly 1 billion years earlier had been created when 2 black holes collided. They came, and that's a time series of the distortions in space-time that were created. But the second row there is the gravitational waves as predicted by simulations where the complete set of Einstein's equations were solved, and you can see how well they match up. And in fact, that allowed us to understand it wasn't just a squiggle, but it was 2 black holes of some 30 solar masses colliding at nearly the speed of light. And this was an incredible story that has been going on for about a half a century. That's an important part of it as well. The actual serious work to predict what would happen if 2 black holes, when they would collide, happened started about 50 years ago. This is the great celebration. That's Ray Weiss on the left and Kip Thorne on the right, co-winners of the Nobel Prize with Barry Barish. So I wanted to point out Germany's role in this, which is really quite extraordinary. That's actually not 75 years ago, but more like 83 years ago or something like that, 82 years ago. The invention of the computer in 1941, the programmable electronic computer, was a major milestone in the development of high-performance computing, in fact, computing itself. And you have both Konrad Zuse and Heinz Billing who worked together on different aspects of this. Now, fast forward some years later, many of you will know or should know of Larry Smarr if you don't know him personally. Larry's PhD thesis in 1975 was the collision of 2 black holes. Very early work, and he needed supercomputers to study it, and they weren't available at the time in America. So Larry wrote what's now known as the Black Proposal, an unsolicited proposal to the National Science Foundation to create what became the first of the national open supercomputing centers in America, and many followed around the world. And I want to point out something from that proposal. he talks about computational astrophysicists have been going to the Max Planck Institute for Physics and Astrophysics in Munich to do their computing, and he points out that I can't get my computing in America. Max Planck is a model for what is needed in the United States, and having later worked at Max Planck, I'm very proud to have been associated with that and Larry's initial point, which is circled right there. So that's very important. That created NCSA and a number of supercomputing centers in the United States. But the point was the black hole problem is actually what drove this very specifically in order to create high-performance computing centers available to open science around the world. That's an early calculation that Larry did. See, it looks quite similar to that waveform that was actually detected some 30, 40, I don't know, 40 years later. I can't do the math in my head here, but quite a long time. So, in the 1990s, this is after Larry had founded NCSA, many things happened. The first computer possible that was large enough to actually simulate the full three-dimensional case of two black holes colliding, the NCSA CM5 512 processors. For me, it was a complete revolution. That is the first three-dimensional simulation in the second panel here of two black holes colliding just head-on. And that little visualization there was carried out by our friend John Shelf here. The National Science Foundation funded a very large project of 8 universities working together to solve what was the so-called black hole grand challenge problem. And then the Albert Einstein Institute here in Germany in Potsdam was founded in 1995. And these are some real landmarks in the development of this entire field. The Albert Einstein Institute itself in Potsdam was one of the original founding directors. So there was a group from Garching that moved up to Potsdam, created this institute, and Bernard Schutz became one of the first managing director of the institute, and it was amazing in what it brought in. So that is a group that I considered my group at the time, with many people, and I don't have all the pictures, but many of these folks went on to become leaders and are still leaders today in this field. I have a few circles around people from that group who were later credited with the actual solution to the two black hole problem, the full 3D simulation of two black holes in arbitrary no symmetry, so just the complete general case. So many of us work together, but those 4 folks are among the leaders. Another group led by Franz Praetorius, or actually Franz himself, had a different approach and also is credited with the big breakthroughs of 2005 that made it possible. So, when you have large collaborations like this, you need people to know about parallel computing, visualization, theoretical physics, numerical algorithms, and many things. So there became an effort to create a software framework that would allow large teams to work together, and I won't go through the details there, but you can see many different iterations on this. This is a picture of a group, the so-called EU Astrophysics Network that I led in the late 90s. That's a picture of about 70 or so of us in Southampton working together. Well, how do people work together? Well, we had to find a framework for people to share codes and be able to work together. And I'm going to shift now to Gabrielle Allen and let her tell about that work itself.
Okay, so this is not viewing. Yes, so there it is. So I'm Gabrielle Allen. I'm also at the University of Wyoming, and I'm going to tell you a little bit about the software that we've developed to solve some of these problems, the Cactus toolkit and the Einstein toolkit. And so, as Ed mentioned, we now have codes that are able to routinely solve black hole collisions for basically arbitrary configurations after a 40 or 50-year effort to develop this. And so one of the pieces of software that we've been using for that Ed mentioned came from the Black Hole Grand Challenge and from the Albert Einstein Institute is the Cactus framework, where we had the first release back in around 1997. And the idea here was to create an open plug-and-play component framework that could take advantage of the growing supercomputers back then. And so we designed something called Cactus with the group that Ed mentioned just there, and had a modular system. We had, I think, well-designed high-level abstractions, since we're still able to use basically the same abstractions today. And the idea was to have swappable components that could be defined by the parameters, the variables, the methods that they defined, and have a Cactus flesh that would bind all these different components together and take care of scheduling, parallelization, and all of those activities. We provided something called the Cactus computational toolkit that provided general components, coordinates, I/O, all of those kinds of things. And then the other thing was that we tried to do it in a way that wouldn't only work for general relativity, realizing that this was a very small community, and so made it usable so that people in computational fluid dynamics, coastal modeling, other areas could also take advantage of the same infrastructure. This was pretty successful, and in this way, this is a kind of layer diagram. The Cactus framework was able to abstract actual implementations of things away from the underlying parallel layer, so that meant that we were able to work with computer scientists like Manish and John, who would develop new, highly optimized driver layers or I/O routines that then could be automatically plugged in and made available to application scientists. The application on their hand would different applications could form different toolkits. I'll tell you in a minute about the Einstein toolkit, with the idea that each application toolkit would sort of share definitions. So it would have a common understanding of variables, parameters, test cases, provide documentation that could help to enable a whole community. And in this way, it made it possible for groups to work either to provide open code, or also to take advantage of all the open code that was there and build their own toolkits for their own groups. And this still works. This still means that we have a mechanism that we can take advantage, that we can easily incorporate. I know as we start to think about quantum computing, or now digital twins and so on, different methodologies can be very easily introduced and made available through the toolkit, keeping the same science routines. And so the toolkit that we're using now, that is we can use routinely for black hole collisions, for neutron stars and other things, is called the Einstein toolkit. This provides open software for the relativistic astrophysics community, and basically provides these core computing tools that make it possible to configure a particular science problem and run it on modern supercomputers. So we have around 200 components that have been written for this toolkit, over 1 million lines of code, around 400 or so users at the moment, who really span across the world at 276 different groups, 49 countries at the last count. And then we have a development team that provide the core maintenance of the code, try and involve the whole consortium in providing help desk support and advice, and try and stick to a pretty rigorous 6-month release schedule for new releases. And in this way, the open code base that you can download from the repository now can solve, you can take it, you can look at black hole mergers, neutron star mergers, mixed binaries, supernova, accretion disks, boson stars, all the kinds of regular, highly relativistic systems that you might want to study. I think the really cool thing, though, is that we try and publish configurations and parameter files for full code, so that people can download it and use it, so that a single individual somewhere can start doing computational modeling of black holes or neutron stars, even if they're in a small group and don't have access to the large computational infrastructure. And so we also have parameter files. For example, you can go there now and download the parameter files so that you can run that first black hole collision that Ed showed the graph for. We've also had fun along the way working to do some computing research, and so we've been able to use this framework where we've really needed to use a lot of computing in novel ways to do some new things in grid computing and distributed computing, remote visualization. We had a lot of fun doing computational steering from mobile phones and portals where you could try and automatically deploy black hole codes and provide grid interfaces. So I think that's my last slide. So I pass on to Manish to tell you more about the computer science.
Right.
Thank you. Okay. Hello, good afternoon. I'm Manish Parashar. I'm with the University of Utah, and I joined this project as a grad student and then as an early PhD, and it has really, in a sense, defined what I've done since in my career, right? And so that's sort of one. I'm going to talk about other translation impacts, but I think one impact, one lesson learned for me is that how important it is to have an exciting problem to attract students, right? That's beyond anything else, right? And it sort of really changes their perspective on research. All right, so as I said, I came in as a graduate student looking at the computer science aspects of the binary black hole grand challenge. And one aspect that I was looking at was how do you support large scale in the early 90s, which was probably 100 processors or so, right? So large scale parallel adaptive mesh refinement. And Ed and Gab can talk a lot more about why AMR was very, very important, but it was critical to be able to do these simulations that this project was trying to do. And so we're trying to build the computer science framework to be able to support that. And a big part of that was coming up with these data structures, runtime systems, load balancing systems on top of MPI that can support this kind of adaptivity, right? Where as you evolve these codes, the areas of refinements move around on this three-dimensional mesh grid, and you need to be able to track the computational load, adapt the data structures, load balance things, and be able to create a code that can scale, right? So there was a lot of computer science underneath this to be able to support this. And on top of that, you wanted to come up with programming abstractions that would allow the computational scientists to be able to, or the application scientists to be able to build their codes. I won't go into a lot of detail, except that we did come up with an abstraction. We called this semantically specialized distributed shared memory. It was a hierarchical dynamic array, distributed dynamic array that would be able to grow and shrink as these adaptive regions evolved. It had a nice array-like semantics which mapped very nicely into the codes that the physics was built on, and we did spend a lot of time thinking about what the runtime and underneath would be. Because this was, the end of the result was applications that were running at scale, building software along of this was so important, right? And so while we were doing a lot of the research and publishing papers, we were also building software to support this, right? And I think that's what I think is the biggest impact from my perspective of this project. And that is the concept of translational computer science, right? The idea of not just doing foundational or user-inspired or applied research, but coupling that with the delivery and deployment of outcomes to the target community, and then having this bidirectional feedback or co-design where you impact the application, in turn, that impacts your research, right? And a couple of years, maybe 3 or 4 years back, David Abrams and I were thinking about this, right? We were in this meeting, and we were seeing this talk, and said, what is different about all these talks? This was a meeting that Jack Dongara had organized, and we realized that all the talks had this characteristic about it, where you're bringing these two aspects together, and we have started this thinking about formalizing this, because it's so important, and unfortunately, a lot of the mechanisms that we have in our research community don't support translational work. So that's another talk, and I can go into more detail, but I think that's one of the biggest impacts of this project. Is one of the earlier projects that was really valuing and emphasizing the translational aspects of the computer science research. And just to show you the impacts of the work we did, right, here are some of the different applications that went on and used this framework for AMR that we built. And it was followed up with a number of publications that supported it. And today, the basic codes, I still get emails about codes, although the codes themselves don't exist anymore, but they are the pieces in that. Because of the open source, you have pieces that have been embedded in other frameworks today. And it's right now underlying some work that we are doing in supporting both coupled simulations on some of the largest machines in DOE right now, in the US Department of Energy, but also in integrating this the experimental aspects with the large-scale simulations, right? And the data structures is itself that came out was very similar to what became popular later on as DHTs, or distributed hash tables, and so on. So I'm going to stop there, and I'm almost out of time, so I hand it over to
Ciao.
Luigi.